In this video, we will look at the Strassen's matrix multiplication. We will first look at the mathematical formula to compute the matrix multiplication. And then we will look at the Strassen's approach using the divide and conquer strategy. The problem is to compute the product of two n by n matrices. Given two matrices A and B of size n by n, compute matrix C, which is the product of matrix A and matrix B, using the mathematical formula C of I comma j equal to the summation of the product of A of I comma k and B of k comma j, where k ranges from 1 to n for all I and j between 1 to n, and n is the number of rows and columns. The resultant matrix C will also be of the size n by n. So, this is the mathematical formula for computing the product or multiplication of two matrices of size n by n. Now let us look at an algorithm. We will call this algorithm as matrix multiplication, which uses four parameters. The first parameter is matrix A. The second parameter is matrix B. The third parameter is matrix C, which is the result of the product of matrix A and matrix B. And the fourth parameter is n, that is the size of the matrices or the number of rows or columns of the matrices. Now, we need to compute each element of matrix C of I comma j. So, within the algorithm, we will use a for loop for traversing the rows I from 1 to n. Then, we will also use a nested for loop for traversing the columns, that is, for j from 1 to n. Then, within the for loop for j, we will initialize c of I comma j to 0. This is because we have to perform summation of the products. Then, the formula contains k ranging from 1 to n to compute the product of a of I comma k and b of k comma j. So, we will have another nested for loop for k from 1 to n. Then within this for loop, we will have the statement c of I comma j equal to c of I comma j plus a of I comma k multiplied by b of k comma j. So this is the algorithm to compute the product of two matrices using mathematical formula for any size n by n of the matrices. Now let us analyze the complexity of this algorithm. This algorithm uses three nested for loops. Each for loop performs iterations n plus 1 times. Therefore, the statements to compute the product of matrix A and B and store the result in C will be executed for n cubed times. Therefore, the overall time complexity of this algorithm will be O of n cubed. Now let us look at the divide and conquer approach to compute the product of matrices A and B of the size n by n. In divide and conquer approach, we divide the problem into subproblems and sub-subproblems until the problem is small and can easily be solved. So, matrix A of size n by n and matrix B of size n by n is divided into four square submatrices. Each submatrix has the dimension n by 2 by n by 2. Then again, the submatrices are divided into four square submatrices until we have 2 by 2 matrices. And when we have 2 by 2 matrix, we say that the problem is small and the problem can easily be solved by using the direct matrix multiplication formula for 2 by 2 matrices. That is, we know that the product of 2 by 2 matrix A and matrix B will be a 2 by 2 matrix where the element in the first row and the first column, C11, is A11 multiplied by B11 plus A12 multiplied by B21. Then the element in the first row and second column, that is C12, is A11 multiplied by B12 plus A12 multiplied by B22. Then the element in the second row and first column, C21, is A21 multiplied by B11 plus A22 multiplied by B21. And the element in the second row and second column, C22, is A21 multiplied by B12 plus A22 multiplied by B22. So these are the formulas to compute the elements of the product of 2 by 2 matrices. Now here we assume that the size of the matrix is n by n, where n can be 2 or 4 or 8 or 16 or 64 and so on. That is, n is the power of some integer k. This is because if n is not power of 2, then when we divide the matrices into 4 submatrices, we will not be able to get a 2 by 2 matrix at the end. So we assume that the matrices are of size n by n, where n is some power of 2. In case the size n is not a power of 2, then we can add enough rows and columns of zeros to both matrices A and B so that the size n is power of 2. So this is how we can divide a large matrix into smaller submatrices until we have a 2 by 2 matrices. Then we can compute the product using the direct matrix multiplication formulas for size 2 by 2 matrix. Now, we need to combine the solutions of these submatrices to get the solution of the product of the original matrix. To have a clear understanding, let us consider matrix A and matrix B of size 4 by 4 and apply the divide and conquer approach. Matrix A is divided into 4 submatrices of size 2 by 2. Let us call these submatrices of matrix A as E, F, G, and H. And matrix B is also divided into 4 submatrices of size 2 by 2. Let us call these submatrices of matrix B as R, S, T, and U. Then, to compute the elements of the matrix C, that is the product of matrix A and matrix B, we can apply matrix multiplication as applied to matrices of size 2 by 2. Therefore, we multiply submatrix E with submatrix R plus we multiply submatrix F with submatrix T to get the submatrix W of matrix C. This is the same multiplication formula we use to compute the product of 2 by 2 matrices. Now, submatrix E is a 2 by 2 matrix as well as submatrix R is also a 2 by 2 matrix, and the product of these two matrices can be computed directly using a 2 by 2 matrix multiplication formula. Then the product of submatrix F and submatrix T can also be computed directly since these submatrices are also 2 by 2 matrices. Then the matrix addition is applied to get the elements of submatrix W of matrix C, which will also be a 2 by 2 matrix. In the same way, to compute the elements of the second submatrix X of matrix C, we multiply submatrix E with submatrix S plus we multiply submatrix F with submatrix U. Even here, submatrix E as well as submatrix X and submatrix F and submatrix U are 2 by 2 matrices, and the product of these two submatrices can be computed directly using the 2 by 2 matrix multiplication formulas. Then the matrix addition is applied to get the elements of submatrix X of matrix C. Now, to compute the elements of the third submatrix Y of matrix C, we multiply submatrix G with submatrix R plus we multiply submatrix H with submatrix T. Even here, the submatrix G as well as the submatrix R and the submatrix H and T are 2 by 2 matrices, and the product of these matrices can be computed directly using 2 by 2 matrix multiplication formulas. Then, the matrix addition is applied to get the elements of submatrix Y of matrix C. And to compute the elements of the fourth submatrix Z of matrix C, V multiply submatrix G with submatrix S plus V multiply submatrix H with submatrix U. Even here, submatrix G as well as submatrix S and submatrix H and U are 2 by 2 matrices. And the product of these two matrices can be computed directly using 2 by 2 matrix multiplication formulas. Then, the matrix addition is applied to get the elements of the submatrix Z of matrix C. So, this is how we can divide a large matrix into smaller submatrices until we have a 2 by 2 matrix, then directly compute the product of matrices using the matrix multiplication formulas for 2 by 2 matrices and combine the solution again using the same 4 matrix multiplication formulas to get the solution of the larger matrix. Now let us analyze the performance of the divide and conquer approach to find the product of n by n matrices. Here, we say that the problem is small if n is less than equal to 2, and the product of matrices can be easily computed using the 4 matrix multiplication formulas for 2 by 2 matrices. And the problem is large if n is greater than 2, that is, if the matrices are greater than 2 by 2. Now, for n greater than 2, the product of two matrices can be computed by recursively dividing the matrices into 4 submatrices of size n by 2 by n by 2 until we have 2 by 2 matrices. And the solutions are combined using the same 4 matrix multiplication formulas used for 2 by 2 matrices. So since we are using the divide and conquer approach, which uses recursion, the complexity of recursive algorithm is computed using the recurrence relation. Let us consider the complexity of this divide and conquer approach is T of n. Then, for small problem, that is, when n is less than equal to 2, we say that it takes constant time b. Since we are using 4 direct matrix multiplication formulas of 2 by 2 matrices to compute the product, which are primitive statements. Then, when n is greater than 2, we divide the matrices of size n into submatrices of size n by 2 and apply 8 multiplications recursively to combine the solutions. So, when n is greater than 2, the complexity will be 8 t of n by 2 plus we also recursively perform 4 matrix additions taking constant time c. And now, since it's matrix addition, that is, each corresponding element is added, therefore, we need to traverse rows and columns of the matrices, which is done in n squared times. Therefore, if n is greater than 2, we have 8t n by 2 plus c multiplied by n squared. And here, b and c are some constants. Now, this recurrence relation can be solved using the substitution method, which will be O of n power log 8 to base 2, which is nothing but O of n cube. So if you observe, the divide and conquer approach also takes O of n cube. Now let us look at the Strassen's matrix multiplication method. The time complexity of matrix multiplication can be improved by using the Strassen's matrix multiplication method. The Strassen's matrix multiplication also uses divide and conquer approach. Now, the idea behind this approach is that, in terms of complexity, multiplication operations are more expensive than addition operations. So if we observe, the 4 formulas for computing the product of matrices takes 8 multiplication and 4 additions. Strassen has discovered a way to compute the product of matrices using only 7 multiplications and 18 additions or subtractions. The Strassen's approach involves computing values for P, Q, R, S, T, U, and V. So let us look at what these are. Remember, we are performing the Strassen's computation on smaller problem, that is on 2 by 2 matrices. So in Strassen's computation, P is the product of the sum of A11 plus A22 and sum of B11 and B22. Q is the product of sum of A21 plus A22 and B11. R is the product of A11 with B12 minus B22. S is the product of A22 and B21 minus B11. T is the product of the sum of A11 plus A12 and B22. U is the product of A21 minus A11 and B11 plus B12. And V is the product of A12 minus A22 and B21 plus B22. Now, once we have computed these P, Q, R, S, T, U, and V, we can compute the elements of the resultant matrix C. So, the element in the first row and first column, that is C11, will be P plus S minus T plus V. The element in the first row and the second column, that is C12, will be R plus T. The element in the second row and first column, that is C21, will be Q plus S. And the element in the second row and second column, that is C22, will be P plus R minus Q plus U. So if you observe, the Strassen's approach uses only 7 multiplications. That is, each in P, Q, R, S, T, U, and V. Now, let us analyze the performance of the Strassen's approach to find the product of n by n matrices. Let us look at the recurrence relation. Even here, we say that T of n is constant B when the problem is small, that is, if n is less than equal to 2. And the product of matrices can be easily computed using the Strassen's equations. Then, when n is greater than 2, we say that the problem is large, that is, if the matrices are greater than 2 by 2. And the product of two matrices can be computed by recursively dividing the matrices into 4 submatrices of size n by 2 by n by 2 until we have 2 by 2 matrices. And the solutions are combined using the same Strassen's equations used for 2 by 2 matrices. So when n is greater than 2, we divide the matrices of size n into matrices of size n by 2 and recursively apply 7 multiplications of Strassen's equations to combine the solution. So when n is greater than 2, the complexity will be 7t n by 2 plus we also have to recursively perform some matrix additions and subtractions taking constant time c. And now, since it's matrix addition and subtraction, that is, each corresponding elements are added or subtracted, therefore, we need to traverse the rows and columns of the matrices, which is done in n squared times. Therefore, if n is greater than 2, we have 7t n by 2 plus c multiplied by n squared. And here, b and c are some constants. Now, this recurrence relation can be solved using the substitution method, which will be O of n per log 7 to base 2, which is nothing but O of n per 2.81. So, the Strassen's approach also uses divide and conquer approach, but the complexity is O of n per 2.81. Here, n power 2.81 may not seem much smaller than n power 3, but since it is the power of n, or the difference is in exponent, the runtime performance is significantly much better when the size of n is large. So to summarize, the algorithm using mathematical formula takes O of n cubed, as well as the divide and conquer approach using the 4 formulas also takes O of n cubed. The Strassen's matrix multiplication also uses divide and conquer approach, but the time complexity is O of n power 2.81, which is significantly better than O of n cubed. So this is all about the Strassen's matrix multiplication.